Welcome, everybody. We'll get started in just a moment. Okay, so I do have 1 o'clock Eastern. Hello, everybody, and welcome to today's American Biogas Council webinar sponsored by Air Products Membrane Solutions, biogas upgrading cycle options for 2, 3, and 4-stage designs. I know that we're all eager to get started with today's presentation, but I have a couple of quick housekeeping items before we do. Next slide, please. We will be taking all questions today at the end of the webinar. That being said, please feel free to ask your questions at any time during the session using that Q&A section located in your bottom toolbar. It's shown on this slide as well. If you have any questions about how to enter questions, please feel free to direct message our staff in the chat. A reminder that you all will receive the webinar recording and slide deck after today's presentation before the end of the week. So thank you again to Air Products Membrane Solutions. And without any further ado, I will hand things over to our moderator, ABC State Policy Manager, Jonathan Harding. Jonathan, please take it away.
Thanks, Erica. Appreciate it. Again, Jonathan Harding, Manager of State Policy with ABC. I really appreciate everyone being here today. This is a really great group. So I definitely want to keep it quick and let you all get to the meat of the presentation here with Leo Nimitz with Air Products Membrane Solutions, and he will go ahead and walk us through the presentation. Take it away, Leo.
Thank you for the introduction. My name is Leo Nimitz. I'm an applications engineer with Air Products Membrane Solutions. And as they said, I'll be talking about biogas upgrading and cycle design options using gas separation membranes. First, to get into Air Products, where today Air Products is a large industrial gas company with over $12 billion in sales. We've been operating for over 80 years, and we operate in over 50 countries. Air Products, we're a leader in the industrial gas space, a Fortune 500 company, and we provide essential industrial gas technologies and applications expertise that enhances our customers' sustainability and improves their operations. As the leading global supplier of hydrogen, we are accelerating the energy transition through clean hydrogen mega projects to decarbonize the hardest to abate industries and heavy-duty transportation sector. Air Products has a proud history of innovation, operational excellence, and an unwavering commitment to safety and environmental stewardship. Air Products has a total safety philosophy. We believe that maintaining a safe workplace is a fundamental and moral responsibility. And we take the approach that all accidents are preventable, and the only acceptable goal is 0 accidents and 0 incidences. And we strive to achieve that goal at every location, every day. So to get into Air Products Membrane Solutions, we have 4 locations. Our headquarters for the Membranes Group is here in St. Louis, Missouri, and that's where we have our manufacture all of our membrane equipment. Our corporate headquarters is in Allentown, Pennsylvania, and then the Membrane Solutions has 2 other office locations, one in Norway and one in China. So a brief history of Membrane Solutions. This group was originally owned by Monsanto and called Permia, and Permia commercialized the first gas separation membrane systems in the 1970s and 1980s. In 1991, Air Products acquired this business and the trademark, and then in 2005-2010 timeframe, we expanded into biogas via our network of OEM system builders. Recently, in 2024, we broke ground on expanding our manufacturing facility, and that expansion will be completed this year. So Membrane Solutions has 4 different business units. prism membrane separators, and that's really what captures our how we support the biogas market. And this unit, we support customers by selling individual membranes to system builders or OEMs and allow them to build systems for themselves or for end users or customers that way. Our marine system is we build systems for maritime shipping, and that can be for fuel safety, fuel efficiency, as well as for enhancement of goods that are being transported through controlled atmospheres. We also have an engineered to order systems, primarily for the refinery space and hydrogen recovery, as well as a global service and support that we provide across all three of these units, or three business units as well. To get into prism membranes a bit more, this is, like I said, this is how we support our biogas upgrading, as well as biogas dehydration, as well as our bio LNG production. But membranes can also be used for nitrogen generation, for air dehydration, as well as for fuel safety on airplanes, and for oxygen generation. So Air Products, today we have thousands of references across all of these different business units and across different application spaces. And so what is a membrane? So the textbook definition of a membrane is a discrete thin interface that moderates the permeation of a chemical species in contact with it. And so that's a membrane separates chemicals based on dimensional differences, size differences, as well as how the chemical species interacts with the membrane material. And so here on the left, we have a gas separation membrane module, and this module contains these hollow fibers. It's tens of thousands to hundreds of thousands of hollow fibers. And if we look at the ends, we can see they are hollow like a straw. And when we talk about a membrane having a thin interface, we aren't talking about this wall here. We actually can zoom in and see the porous support as well as this outer edge. And if we zoom in again on the edge here, this skin thickness is what is doing the separation in a gas separation membrane. And that skin thickness is on the order of 0.1 microns thick. So extremely thin. So as I said, Air Products, we make polymeric hollow fiber membranes, but membranes can be made of other materials beyond polymers, including metals and ceramics. And they can also come in different forms like flat sheet or spiral wound, as well as our hollow fibers. I talked about one application already of gas separation. So membranes can be applied to gas separation, either for nitrogen production, carbon capture, hydrogen recovery, as well as for biogas upgrading. But membranes are also used in water treatment, dialysis, fuel cells, and gas liquid contactors. So how does a membrane work? Well, we measure how fast gas can permeate or move across a membrane as permeability. And permeability is comprised of two parts, diffusion and solubility. Diffusion is related to how the size of a molecule and how fast it can move, or related to the size of the molecule, typically where smaller molecules can move faster. Solubility is really how does the molecule interact with the membrane material. And based on these two parameters, you get relatively fast gases and relatively slow gases. The greater the relative difference, the easier gases can be to separate. And so let's look into diffusion of gases a bit more. As I said, this is primarily a function of size, where smaller molecules can move more quickly. And just to kind of highlight this with an example here is, if you think about who could move through a crowd of people easier, a mouse or a cow? And the answer is a mouse could move through easier. It's smaller, people won't notice it can fit through all of the spaces. It just is going to get across faster. If we then go to solubility, this is, if you think back to chemistry classes or that, this is how molecules interact, and those interactions could be described as like polar interact or non-polar, hydrophilic versus hydrophobic. Solubility temperature also plays a big role here, and it's important to note too that solubility can have a larger impact on the gas separation than molecular size. And so to highlight this, again, if we think about our example of a mouse and a cow, but now we think about a mouse versus a bull, which could get through a crowd quicker. Well, the answer is the bull could. You can think about it as the horns change the interaction between the crowd and the bull, allowing it to make way and get through much quicker. So what does this look like on the molecular level? We start with our feed side, which is high pressure. Our gas comes in contact with our membrane. Molecules sorb onto the surface, diffuse across the membrane, and then desorb from the membrane at low pressure on the permeate side. Um, this is this is this physics is described by this equation here, the flux equation, where this is how much gas is permeating. This is the permeability. Your driving force is the partial pressure difference. So this is the concentration of the gas on the high side, as well as times the pressure, minus the concentration and the pressure on the low side. And again, here, L is our thickness of the membrane, which is the skin thickness, which again is on the order of 0.1 microns or smaller. We also, when we talk about gas separation, we don't want to think just about how fast gas can pass across it. We want to think about how efficient the separation is. And so for that, we talk about alpha or selectivity, which is a ratio of the permeabilities of the gases you're trying to separate. If we want to look at if we want to look at a real world example of sorption, we can think about a sponge and how the water sucks up the water when it comes in contact to it. And then for diffusion, you can think about making a cup of tea. As you set your tea bag in and you brew your tea, that sort of diffuses across or throughout your water to give you a strong cup of tea. And then for desorption, that happens anytime you open a carbonated beverage. The CO2, the foam, the CO2 release is the gas desorbing from the liquid. So if we go ahead and apply this to biogas or to what does it look like in a hollow fiber membrane, we zoom in on our membrane into the fiber bore or the inside of the fiber. Our biogas mixture is fed through the bore. Our fast gases like CO2 and oxygen permeate across and are collected on a low pressure permeate side, whereas your slow gases like nitrogen and methane are concentrated and collected in the non-permeate at pressure. And so we're talking, as I mentioned earlier, how well you can separate a gas depends on their relative permeability. So fast gas like hydrogen and CO2, these two gases would be easy to separate from nitrogen and methane, whereas gases with similar relative permeabilities like methane and nitrogen are not separated well by membranes, and typically methane and nitrogen are not separated by a membrane. So moving on to how do we apply membranes to biogas? And so when I talk about biogas, I'm talking about a mixture of methane and carbon dioxide formed from the anaerobic digestion of organic materials. And that can be done in a digester or it could be done in a landfill. There are byproducts from the bacteria breaking down organic materials aside from the methane and carbon dioxide. There's also H2S, ammonia, VOCs, and sometimes siloxanes. It's important for membranes to last a long time to remove your VOCs and siloxanes. And that's typically done in pretreatment by carbon bed or a carbon bed and carbon filter and particulate filter. Removing these things will ensure membranes last a long time and that they perform as they were designed to. So if we look at our sort of the simplest system you could build with a membrane is a single stage system where your feed gas is sent to a group of membranes. Your slow gas or biogas, and it's going to be methane, will concentrate in your non-permeate, whereas your CO2 will concentrate in your permeate, the reject gas or vent gas. And here we have just kind of a group of membranes and what a single stage or what any stage in a multi-stage system will look like. And so one stage membranes work for upgrading, but they face a challenge in that the methane purity and methane recovery can't be controlled independently. And that I mean that if your goal is to increase your methane purity, you have to remove more gas. And as you remove more gas, you'll also lose more methane to your vent. And so your methane recovery goes down. In the same way, if you want to increase your methane recovery, you have to remove less gas, which means that your purity will go down. And so this isn't typically this isn't a very viable option for biogas upgrading. So what are some of the ways that we can improve our system to enable membranes to be more successful in biogas? Well, the first option is a two-stage system. And here, this typically the recovery you'll see for a two-stage system is between 93 and 97% methane recovery. And so this works. Your feed gas is sent to your first membrane. This first membrane does a kind of a rough cut. It splits your gas into mostly methane and mostly CO2, whereas your non-permeate, it's mostly methane, is sent to the second stage. This second stage is used to polish and bring the methane content up to the required specification while recycling gas back to the upstream of your process. Your first stage also sets the recovery because this is the only place gas is removed from your system, and that will be a CO2 rich stream. So we have one of our references that started up recently is in India. It operates a two-stage system at 15 bar gauge, achieves greater than 97% methane recovery, and they have a flexible operation to achieve either 97% methane or 99% methane. And it depends on their specific customer. In India, they typically take the biomethane product and compress it into gas cylinders. And they can use those cylinders either for cooking, which doesn't require as high purity methane, as well as they can go to CNG for vehicle fueling, which then it does require the higher purity. Um, yeah, and so let's look at some comparisons of changing our output parameters, our methane recovery and methane purity. So if we think about a biogas stream containing 60% methane and 40% CO2 operating at 20 Celsius and 16 bar gauge, our first column here is our base case of 97% recovery and 99% purity. We can see the impact of decreasing our methane purity to 98% while maintaining the same 97% recovery. Overall, the relative number of membranes required decreases, as does our power consumption. If we contrast that then and look at what happens if we maintain our purity and increase our recovery targets, this ends up resulting in an increase in membrane area and an increase in power consumption. And then our last column shows again our methane recovery being increased versus our base case versus our purity being decreased. And we can see that there's savings in membrane area or the number of membranes required, but an increase in the power consumption. And so the two-stage system works really well up until that 97, 98% methane recovery. And then once you want to increase your recovery, it's best to move on to a three-stage system. This is sort of a basic three-stage system. It's pretty widely used. But again, you start with a feed gas that goes to your first stage, which does your rough cut. Your second stage does your polishing and produces your biomethane at the purity you require. Where the difference here is this third stage is added, and this third stage recovers the methane that would have been in your first stage permeate and recycles it back to the beginning of the process. It also then produces your vent gas or your CO2 rich reject gas. Um, and so, as I was saying, this is one of the more common design choices OEMs make. And just want to give a reference here. We recently, I think in the last year, this system started up in Europe with, it's just one of our 200 references in the biogas space. And their target was grid injection. They're operating at 17 bar gauge, achieved 55 or less than 55% recycle, and then the 99.5% methane recovery and less than 1.3% CO2 for their product. So beyond just the basic three-stage design, there's a couple of pieces of equipment that you can add to enhance the performance or shift your cost between operating and capital cost here. And one of those things you can do is you can add a blower here between stages 1 and 3. And this blower allows you to operate your first and third stage at greater partial pressure differences. And that, as we saw earlier, will increase the driving force across your membranes. And this really sees a major benefit in reducing the number of membranes required for the system to function. One other piece of equipment you can add is a vacuum pump on your vent gas or on your reject. And that similarly has an impact that it allows you to operate your first and third membranes at greater pressure ratios or with greater driving force in those. The major difference here is a vacuum pump tends to have a bigger impact on recycle compared to the blower having an impact on membrane count. And so just to go back without those pieces of equipment, see the typical three-stage design here. And we're going to compare now our three-stage system with our 60% methane, 40% carbon dioxide feed at 16 bar, 20 Celsius, targeting 99.5% methane and less than, or with a product purity of 98.75% methane. So our base case is the standard or basic three-stage design. We can see that if we add a vacuum pump, there's a slight decrease in membrane area, but really the savings ends up being in power consumption and the reduction of the recycle. Whereas an interstage blower, you can see a more significant savings in membrane count, where your power, there's a slight change in power here as well. So three-stage systems work really well up until this 99.5% methane recovery. But as regulations start to target methane slip or methane emissions, it may be desirable to move beyond 99.5% methane recovery. And to do that, Air Products has a proprietary four-stage design. And so this design really focuses on extremely high recoveries that can be influenced by regulations. So here, again, we have our feed gas. Our first stage still performs the same task of doing an initial separation. Your second stage does your polishing and produces your biomethane. The second stage permeate is still recycled back to the beginning of your process. A difference here is that first stage permeate is recompressed before it's fed to the third stage. This recompression allows the methane-rich non-permeate to be sent back downstream of the compressor, and meaning that this gas, the feed compressor doesn't have to recompress this portion of the gas. Then your permeate is sent to a fourth stage. The fourth stage recovers any methane left, sends it back to the feed inlet, and you produce your CO2 rich reject gas. Just kind of want to highlight again here that this is really for ultra high recoveries, the 99.7 to 99.9% recoveries. And it can target a range of purities depending on what's needed. And really the advantage here versus a three-stage system is the minimizing the total power consumption. As well as depending on the product purity, this second stage can be optional depending on how much CO2 needs to be removed in the first stage. So let's compare our three-stage design, just the basic three-stage design, to Air Products' proprietary two-stage design. And so we can see we're going to target our 99.8% methane recovery at 98.75% purity, and are still using the three stages as the base case. If we operate a four-stage system with only a single compressor, there's no change in power consumption, a slight change in area. We can reduce the change in area by increasing the pressure from our compressor, still using only a single compressor. So we get the same area requirement as a three-stage design, but no real power savings. When we add the second compressor, there can be an increase in area, but there's significant power savings. And this is really the benefit of the two compressor design is over the life of your plant, you'll have lower operating costs the entire time. And so if we want to look at now, what else can we change beyond just moving between two, three, and four-stage designs? What can we change within a system itself? We can look at some different process variables and what their impact might be. And so these first two, these are sort of changes that could happen based on how the digester is operated, if there's a change to the feedstock, and so if you produce more biogas, a higher biogas flow, typically you need to increase your membrane quantity or the number of membranes to achieve the same performance. Whereas if you increase the methane content of the biogas, you can have a lower recycle as well as lower power or lower membrane count. Then if we look at kind of the target product specs here, the methane recovery or methane or the biomethane purity. Your methane recovery, if you want to increase your recovery, generally that requires an increase in recycle and a decrease in membrane count. Whereas if your target is to increase your biomethane purity, your recycle and membrane count will increase. While you're looking at designing a membrane upgrading system, you can pick between more selective and more permeable membranes. So higher selectivity will give you a lower recycle, but an increased membrane count. Whereas if you focus on having a more permeable or a more permeable membrane, your recycle won't have much impact, but your membrane count will decrease. And finally, while you're operating a biogas system, having an increase in pressure typically results in a lower recycle and less membranes being required. While for a change in temperature, an increase in temperature typically increases your recycle, but it decreases the number of membranes required. So Air Products, we've been a pioneer in the membrane space, and we continue to innovate in this space. We've operated our own systems across a number of different applications and supported OEMs in developing their systems and have experience in over 4,000 different references across the membrane space. We really value our design partnership and supporting our OEM network globally through our applications and engineering support. Just before we move on to the Q&A, just want to point out that you can learn more at our website, membranesolutions.com, and feel free to reach out to myself, Leo Nemitz here, or our product manager, Kyla Dewey. Both of us will also be at Biogas Americas next month, so look forward to meeting some of you and connecting with you there. Thank you.
Thanks for that, Leo. We do have some questions lined up here, so we'll go ahead and get into those. All right, starting with the first question here. What is Air Products membrane lifetime?
Yeah, so our membranes life, it depends on pre-treatment and ensuring that we have good pre-treatment. With proper pre-treatment, membranes last a long time. We typically say it's on the order of 5 to 7 years. We have had systems operate much longer than that as well.
All right, thank you for that. The next question we have, the permeability of gases showed that CO is a slow gas. Will it be removed in CO2 membranes at all or concentrated in the retenate?
So this sort of separation, CO2, it'll depend a little bit on the specific membranes. This is sort of just representative of it. If you were to do carbon capture or think about CO2 separation, the selectivity is probably not very high, so you would get some removal, but not very much.
Awesome. Next question is, what is the mechanism by which siloxanes degrade the membrane? And forgive me if I don't pronounce some of these chemicals or different things correctly.
Of course. Yeah, so siloxanes, you can think about it as they follow the membrane. Siloxanes are large, heavy molecules. And so polymers are, I think if I go here, you can sort of see like this is a scanning electron microscope images. You could see how they're sort of that web of polymer chain. Siloxanes will end up getting stuck in those spaces and within that space and thus blocking the path for other molecules. So you could think of it like fouling the membrane.
No, awesome. Thank you for that. Let's see here. Next question is, does Air Products offer different membranes with different selectivity / permeability?
Uh, yes, we do. We offer in the biogas space, there's two different membranes. We offer one that is a higher selectivity and one that is a higher permeability. And I kind of pointed out some of the trade-offs there at the end. When a customer comes to us and talks to us about what they need, we'll provide them those options and show the trade-offs for their specific case and allow our system builder to make the decision for what's best for them in that for their customer in that specific application.
Next question. Does a 3 or 4 stage system remove oxygen?
There will be some oxygen removal from any sort of system. Oxygen, it's a bit slower than CO2, but it's a bit faster than your methane. So there is some oxygen removal. Yeah, I think any design we've talked about today will have some oxygen removal. It'll depend mostly on the oxygen that you feed, what concentration you're starting from, and then what your target is, as well as what sort of flexibility you have around methane recovery. And the reason for that is as oxygen sort of splits evenly between non-permeate and your permeate, the more gas that you're able to remove, the lower recovery you have, the more oxygen rejection you'll get as well.
Awesome. Next question. How does Air Products treatment differ compared to other technologies available?
Uh, yeah, I would say that membranes have a few advantages over um, in general. There's no moving parts within a membrane. It's a static piece of pipe filled with our plastic straws, essentially. Um, they're minimal maintenance as well for membranes when you compare to other technologies for biogas upgrading. Um, yeah, I think that's my answer for that question.
Oh, great. Um, how much of the produced methane is needed to supply the energy requirement of a four-stage system?
Um, I'm not going to have an exact number for you, but you could see that within a four-stage system, your power consumption for the high at the high recovery is less than a three-stage system operating at that same condition. So just by a comparison here, your power consumption will be lower than a three-stage operating at the same space once you are in that high recovery, the greater than 99.5% range.
Do your membranes handle H2S?
Yes, we have our membranes are resistant to H2S. We have systems that are operating now we're at 7 years and they've been operating continuously in H2S environments between 3 and 5,000 parts per million H2S for the life of the membrane, and they're still performing as designed.
Is there a minimum flow rate for the four-stage design?
Um, stage, I think. Uh, I don't know what it is off the top of my head. It'll probably vary depending on the amount, the mixture, this methane CO2 mixture that you're feeding to it. There is a there is some minimum just because if you don't supply enough gas to a membrane, all of the gas will permeate across. But I don't know what that is. If you reach out to us with an example of that, we can provide some more numbers to that.
What would you recommend other than a coalescing filter is best to remove any oil carryover from the feed compressor?
Yeah. So coalescing filter is a good start. I think my understanding, some compressor vendors are able to provide, as part of the compressor package, a way to minimize or prevent oil carryover, which can include chilling, uh, chilling the gas stream or chilling the gas oil mixture after it's been, or chilling the gas in after the compressor. So compressor, chiller, reheating, coalescing filter. You can use a activated carbon bed and then a particulate filter before the membranes, and with that combination of things, you should be able to achieve 0.01 milligrams of oil per meter of gas. There's an ISO specification for that as well. If you reach out again, I can provide that number. I don't remember the ISO spec offhand.
Next question. I'm not familiar with these membranes. Why must be set a bunch of filaments instead of a whole cylinder of porous, suitable material?
Uh, could you repeat that question? Is the
Sure.
question?
Let's see here. Why must be set a bunch of filaments instead of a whole cylinder of porous, suitable material? And we can always come back to it if we need
Yeah,
to.
I think the if the question is um I mean, so for first part, Air Products would supply a whole module. This assembly itself is what we sell, and so the that contains the fiber. Um, and the question is why do you, yeah, I might have to actually see that question.
It was at 1:33 p.m. if you need to go to the timestamp.
Oh, um, to me, this question sounds like why would you have the filaments rather than like a it sounds like it's describing the way I'm reading it, it's describing why would we have fiber instead of like in adsorption, you have a packed bed or a material there that your gas flows over, and the adsorption actually grabs onto and holds onto part of the material. And so my answer to that is membranes are, you can continuously operate a membrane. The fiber itself isn't attaching to or grabbing onto the gas itself. The gas is flowing across the membrane, along the membrane, coming in contact with it, removing the gas that we don't want, or in this case, the gas we don't want is CO2 that permeates across. And so membranes don't require regeneration, where a PSA or a sorbent material does require that regeneration. If that's not your question, reach out and we can set up a quick call to discuss more.
No, that was great, Leo. I think that was, yeah, apologies if I wasn't communicating that correctly. It may have been beyond my understanding, but no, that was a great job. Is your product exchangeable with Evonik membrane if the size is the same?
Uh, that's a good question. Certainly, from a system level performance, we can achieve the same or similar performance. Um, there might be some minor tweaks to make, but I believe the answer would be yes.
Does Air Products also offer entire system designs and supplies, or only the membrane modules?
Within the biogas space, we only offer the membrane cartridge or the membrane module. Um, if you're interested, we can recommend some of our OEMs or system builders who would provide a full skidded system.
In the four-stage example, the operating temp is 20 Celsius. Is that constant across all four stages?
That's a good question. Not necessarily. When we talk about our 20 Celsius, it's typically relating to the gas fed to the first membrane. And so the, well, here it's to the first membrane and to the third membrane because we have heat exchangers after the compressors. But your second stage membrane will probably be operating a bit colder, and the same for this third stage membrane as well. And that's I think I highlight on my last slide as well that temperature is a variable that we can um, change or optimize for customer needs. So if we can increase temperatures in different spots to get benefits there of either decreasing the membrane count or changing your influencing the the amount of gas that's recycled. So the is everything operating at 20 Celsius? Not exactly. It's the first and third stage, and then that temperature can be optimized per customer. Typically, 20 Celsius is usually a good starting spot for that conversation about where should we be moving temperature.
Got it. When using the membranes for H2S removal, does it shorten the life of the membranes when compared to those that do not see H2S?
No, H2S does not have an impact on membrane life.
What is the recommended pretreatment for landfill applications upstream of the membranes?
Yeah. Yeah, landfill gas certainly has more VOCs compared to anaerobic digesters that are using crop waste or animal waste as the feedstock. Um, Typically, the recommendation would be a lead lag carbon bed, and that allows you to monitor the concentration of your VOCs between your first and second carbon bed and ensure that once you have breakthrough in your first carbon bed, you can switch and regenerate your first bed while your second bed is still online. And that's uh, typically that's the most common thing I've seen for the VOC removal, siloxane removal, VOC removal.
What is the minimum and maximum pressures to operate the membranes?
Uh, yeah, so for our biogas membranes, the maximum operating pressure is around 17 bar gauge, and the minimum you really have to be above. The higher the pressure, the better your performance. And so somewhere around 7 or 8 bar gauge is required. There may be some cases where uh, if you're using a single membrane stage for polishing or kind of that final upgrading off of something else, where you might be able to operate at between 4 and 7 bar gauge, but your efficiency is going to be quite low.
And you may have answered part of this question at the top of the Q&A portion regarding lifespan, but how often would you need to clean the membrane and or replace it?
Yeah, I think that really is pretty similar to our my answer about lifetime. As long as you have proper pre-treatment, there isn't really any maintenance required on the membrane, cleaning wise or other replacements. Typically, again, you're talking about 5 to 7 years with that's really where I see the that's really where I see the minimum with proper pre-treatment. Yeah.
Excuse me. What's the selectivity of your membrane?
We don't disclose our performance properties publicly.
All right. When your company sells a membrane, do you sell the membrane only or both membrane and case?
Both membrane and case. So I think as we see here, if biogas would be this here on the right, you would get this whole assembly. We have a variety of sizes depending on the application as well. But you get the whole case.
And then how much N2 can you remove from CH4 slash biogas?
Um, Basically none. Nitrogen and methane. I think if we go wrong way. I mean, if we look at the molecular size difference between nitrogen and methane is less than 0.02 nanometers. So their diffusion is nearly identical. And then in solubility, they often have similar solubilities across polymers. So nitrogen and methane separation by membranes is not really um, it's not really possible. There's a few polymers that exist that can do the separation, but it's very inefficient and um, typically not done by membrane technology. So for air products, you essentially don't separate them.
How much of the produced methane needs to be used to provide the energy requirement of a three-stage system?
Uh, that's a good question. I don't really have an answer for. I don't know how much if you were to use part of your product stream to produce that, but um, kind of give a estimate here of like your power consumption in kilowatts per meter of raw gas. Um, if it's something that's not sure if that's really an answer to this question, but it's that's a little bit outside of my expertise.
Which are the worst box for the membrane? What quantities should you avoid?
Yeah, so VOCs, typically we've seen thing like aromatics and alcohols tend aromatics, alcohols, ketones tend to be the most detrimental. Um, Concentration wise, it really is going to depend on if you talk about individual VOCs or if you talk about mixtures, as a mixture of VOCs can have compounding impact. Like having a ketone on its own could be one order of magnitude, whereas if you have a ketone and an alcohol and an aromatic, the impact there could be significantly greater at lower concentrations. Um, so typically, we recommend having um, less than 0.01 milligrams per normal meter cubed of VOCs. That's sort of related to the ISO spec I mentioned earlier.
Great. And then yeah, I can't remember. There's a similar question to this, but let me just double check here. What kind of pretreatment is required after the second compressor?
Yeah, so in a four stage, it would be similar to what we would recommend before the feed compressor, which is essentially a heat exchanger to cool your gas and reheat your gas after the um, compressor, cool it to remove any water that has condensed and reheat back to your operating temperature. And then and then either a coalescing filter or other oil removal like a carbon filter or particulate filter.
Does Air Product offer to take used / end of life membrane modules back for possible refurbishment? And if not, what is the possible pathway for some kind of recycling or repurposing of these membranes?
Yeah, Air Products does not take membranes back after they've been used. Recycling wise, I mean, the shells are varying metals, and so you can recycle the metals, but internals are plastics, and they're not reusable in the sense that, like, if you were to the manufacturing process, at least for membrane manufacturing, couldn't reuse the material to make new membranes. So I don't have a answer for them on reuse of the internal components, but the shells being metal are could be recycled for metal recycling.
Right. Um, we are currently using 6-inch Avonic membrane to upgrade biogas. If we want to switch to Air Product membrane, is it possible to swap the membrane only?
That's because they use a cartridge design. I mean, I think if you look at the rack assembly here, we also have a 6-inch diameter, 5 foot long membrane. Um, so I think the answer is yes. You could use, yes, you could make the switch. Um, if you want to reach out to us, talk about more about your specific system and what you're looking to see with the change, that would probably be a good first step. And then from there, we can talk about sharing dimensional drawings, and that sort of thing.
Great. And just a reminder to everyone, if you have any last questions, feel free to put them in the Q&A section. We're getting to the last couple of questions here. We have a few more minutes, but if you have any burning questions that you have not submitted, feel free to put those in the Q&A section. Let's see. And this might be similar to the other VOCs question, but what is the total ppm of VOCs allowed in membrane feed? VOCs as measured via TO-15.
Yeah, so before I gave an answer in milligrams per normal meter cubed of gas, and that's to account for weight differences between membranes, which it impacts their parts per million measurement. And so the zero point zero 0.01 milligrams per normal meter cubed of VOC is still going to be my answer here. It just is the best way we've found to communicate the level of VOC that's acceptable across all of the ranges of VOCs that can exist.
And then let me see here, going through the last few questions here. Compared to membranes in the field, does Air Products offer a competitive price point per module?
Of course. um, yeah, I think, like I said earlier, like Air Products, we've been operating membrane system. We've since the 90s. The business unit itself has been operating and had commercial success since the 1980s, including the first commercialized gas separation system. And so I think when you look at that, as well as just kind of our references across the space here, across biogas, process gas, nitrogen systems, marine systems, um, we have to be we have to be. I think not only does like our history and operational excellence and the support we provide add value to this, but we have to be competitive in that space as well.
Great answer. Um, this might be the last question, and then we'll wrap up with just a few reminders for future events, as well as thanking Leo for this presentation. Do your membrane products contain PFAS?
No, we do not. There is no PFAS in our products. Um, we have extensive internal reviews to ensure we're complying with regulations, both existing and potential new ones. And so we've made sure that that does not impact our manufacturing process or our products.
Great. Leo, I'll turn it over to you for any closing words on your end, and then I will close us all out with a few reminders.
Yeah, I just want to thank everyone for joining. And again, if you have any questions that we didn't get to, reach out to myself or Kyla. You can learn more at our website. And both of us will be at Biogas Americas next month. So really looking forward to meeting some of you there.
No, thank you, Leo. This has been such a great presentation. Thank you, everyone, for attending, the thoughtful questions. I learned a ton just being able to moderate this, so I appreciate the very engaged attendees as well as Leo's presentation. Just a quick reminder, the slide deck and recording will be sent out at the end of the week. And also, we hope to see everyone, like Leo mentioned, at Biogas Americas in Detroit in a few short weeks. It's going to be May 18th to the 21st. And then please be on the lookout for future trainings offered by ABC and do not hesitate to sign up. Thanks everyone for attending.